Let me begin the afternoon session. Well, the goal is to at least introduce Serre duality. And apply Serre duality. Very important thing, which I will call SD. For example, to prove what is usually called the Riemann-Roch theorem. Riemann-Roch theorem. In the one-dimensional case. This theorem was not proved completely by Riemann because he did not have the analytic tools to do it. Not quite. That's, of course, a long, famous story. And the first proof I read is written in Hermann Weil's notes, lecture notes of Göttingen, which were published very early, 1913, I think. Beautiful. I've told you many times I like it very much. So, and there's a modern English translation I think you would appreciate. That is the one-dimensional case. Two-dimensional case, algebraic case for algebraic surfaces was proved by Max Noether also around the turn of the century, into the 20th century, the algebraic case. And in the case of Riemann surfaces, every Riemann surface can be realized as an algebraic curve. I told you this, and we can see the proof today. But in higher dimensions, this is definitely not true. Many things are simply not algebraic. So we needed a highly analytic version of Riemann-Roch theorem in higher dimensions. This theorem is called the Atiyah-Singer theorem, and is proved using a lot of tough methods of analysis and K-theory and various other things. So it's very tough. So the first easy theorem is Riemann-Roch theorem, and the only content except for the finite dimensionality of the cohomology groups is Serre duality. Dimension 1, all we need is Serre duality and finiteness of the spaces. Okay, so for this we need, at least I need, for an analytic presentation, I need the Domol-Grothendieck isomorphism. So I remind you what, I introduced this morning, but let me just remind you what that is. And let me just say it in a complete generality. For example, you have a holomorphic vector bundle, and E is the sheaf of germs of holomorphic sections of that vector bundle. And you can regard it as, so these are holomorphic sections, or the sheaf of germs of holomorphic sections. And you can regard it as a subsheet of the C infinity sections, locally, local sections. And then, of course, here the D-bar operator makes sense. So you have mappings to 0, 1 forms, C infinity, 0, 1 forms, etc. 0, 2 forms, and so on. Now, this is a very important thing. I mentioned the three things that are important about this. This ends, let me just end it here, this ends dimension. Several things are important. One formal point is it's important. As you know, d squared is equal to 0, and d is d plus d bar. And then you multiply this out as operators. This is d round d plus round d d bar plus d bar d plus d bar squared. And you see, if you apply this operator, the image gives you forms of type 2, 0, 2, 0, because you only differentiate and get dz terms. This operator gives you forms of type 0, 2, and these operators here give you forms of type 1, 1. Differentiate one time with respect to bar, and then another time with respect to z, you get a 1, 1 form. These are the types of these forms. And so, since this thing is 0, and the types, each of the individual types have to be zeros, it follows that this is 0, d bar is 0, and the thing in the middle is 0, which says that d bar equals minus d bar d. Those are the fundamental operators of complexity. Mia, you don't like this?
No, you wrote it. You wrote it wrong.
I did? How did I write wrong? Is there something wrong here? No.
No, because the first two are 0 and the others two have no link to.
Oh, I forgot to write this. I forgot to see. Right. Okay, so these are these operators. Thank you. So that's the first thing, is that this thing here is 0, and so this is complex, and this is called the Dolbeau complex. Complex means exactly that. And the second point is, and this is fundamental, and you have to prove it, is this is an exact sequence of fields. Those are the things you need. You need to get started in this theory. So locally, this means locally it is exact. Let's see what it means. It means i.e. for u appropriate. I'll say what that means later on. So it follows that given a form, say, beta in say a Q form, the coefficients in the bundle on an open set U with d bar beta equals 0 given, there exists alpha of one less form, so a Q minus 1 form, with coefficients in the bundle on U with d bar alpha equal beta. Okay. Now remember, for the Poincare lemma, you require, say, star-like region, and then you have that for the D operator. Here, the condition will be analytic, complex analytic as well as topological. So I will now indicate some of that. This theorem here, this is a theorem, it's called a lemma, and this lemma is called the Dolbeau Gromfeld lemma. It's not very hard to prove, but it's obviously very important. And it's for U equal a polydisk. So a product of n disks. It doesn't matter what radius, of course, just a product of n disks. It's true. Okay? And it is simply not true for just some domain, and it's true for any domain in the complex plane, and I will prove it for that, but it's not true in general. For just any domain.
But you can shrink upwards.
It has nothing to do with shrinking, it has to do with the complex analytic feature of the domain.
Right.
So, in dimension 1, any domain,
Right.
no problem, not even topological, you use a solid problem. Dimension higher, the domain must be what we call holomorphically convex. It must have a good exhaustion, what we talked about this morning, by some strictly subharmonic function, something. It's a complex analytic condition. And you shouldn't be surprised because, I mean, we're dealing with complex analytic cohomology. So, okay, so let me prove what Dolbeau himself proved. Grothendieck then generalized it. Proved this in the 50s sometime. It's a very useful lemma. So for U, any, maybe I have to say, let's look, maybe it has to be connected. I don't think. So U, any open set with a complex plane, it follows that given a smooth function on U, say H on U, there exists a smooth function G. This is the elementary lemma. So in AU, such that the partial derivative of G with respect to Z bar equals H. So, okay? So that's all you need to check. You see in dimension 1, this whole thing stops here. So every 0-1 form is closed. So really you have to only show something here. So that's really exactly all you have to show in dimension 1. Do you understand the statement? It's completely, it's not understood. Okay. This is called the inhomogeneous Cauchy-Riemann equation. In this case, it is not overdetermined and is not difficult to solve. Inhomogeneous Cauchy-Riemann equation. Now here's something you can do in dimension 1, or equivalently in top dimension of the manifold. Step 1 for this, so I'll give you proof. Step 1 of this is take H and take chi to be a cutoff function. On U. So here's the situation I like to draw. Here's U, something like this, and here's, say, the rest of the complex plane. And we have some really odd boundary value for these functions, some weird function on the boundary. So you have some terrible function on the boundary, and something like that. That would be the given function H. And then you cut it off. And so here you don't change it at all. And then you cut it off with chi and extend it by 0. So this is chi times H. All right, you cut it off and then you extend it to be 0. This is a function, I don't know. Let's call it H hat. So this function has compact support. This is the point. It exists on all of C and has compact support, so you're not afraid of anything. Right? So Dolbeau's idea is very simple. You just write down the solution to this problem. And you're not surprised because you can use Stokes and Cauchy type thinking. So the function, let's say g hat, it's not going to solve our problem because I cut this thing off, but at least I'm going to come close. G hat of zeta is 1 over z, 2 pi, the usual thing. Let me emphasize, emphasize where we're integrating over c of something. So what we're going to integrate here is h hat of z, dz bar. So don't get confused here. This is an integral over the surface. You know Cauchy integral formula and so on, but this is not an integral over the boundary of anything. This is an integral over surface divided by z minus zeta. And now you check it. This thing, of course, C blows up here when z equals zeta, but this singularity is still integral. It's really not even there. Okay, and you just simply check by elementary checking that you got the thing here. Then, okay, so that's step one, and it's a standard thing. I show it because it's a standard technique in geometry to take something with a wild boundary behavior, cut it off, and at least solve that problem. There is an important thing to note here. You start with H of compact support, and you get a G, and if you look, G will not have compact support. Okay? So this is an interesting thing. It says, even though you have no cohomology, you have high-level cohomology with compact supports. Cohomology with compact supports means, given a problem with compact support, you should solve it with compact support. So this is an example where the cohomology with compact support is infinite dimensional. But you will see I can solve every d-bar problem for a domain. So anyway, that's what you do. Now let's, just to give you a good experience, you people who had function theory in one complex variable. Yeah. So let UN be a Runge exhaustion of U. I'm only bothering to explain this to you because you need to learn some technology. This is standard technology in complex analysis. This means that, well, of course, UN increases to U. It means that UN is relatively compact in UN plus 1. So you have some weird domain here with some non-trivial topology, right? I don't know. And then you have inside it here is maybe something like here is here's something that won't work because that doesn't have compact support. That's terrible. So I know what I'll do. I'll just do something outside. So that's outside. So that's a set. That's maybe UN, United Nations. Here's the United Nations. Right. There's something really good. Some set that's going out there. And now that's UN maybe. And the set that's bigger is UN plus 1. So UN plus 1 should be bigger than this. Here it is, being bigger, all compact. Bigger. It's bigger here, maybe. I don't know, something like this. I don't know, I don't care. It's slightly bigger with compact bigger. So it's an increasing sequence. It's relatively compact than the other. This is a trivial thing. This is nothing. Right? Anybody can do this. But it's Runge. And Runge means that, so let's let Kn be the closure of Un. So that's compact. And it means that the restriction map realizes Un plus 1 as being dense in Kn by restriction. You understand what I've said? You have an open set,
It's
a
UN.
small
I think.
open set, its closure is compact, you restrict a function, you can, okay, that's the mapping. It's dense, and I emphasize here in this compact set. That means a function is holomorphic on the compact set means it is holomorphic in the neighborhood of that compact set. And it means that you can approximate any function which is holomorphic in the neighborhood of that compact set with a function that's holomorphic on the bigger set. Okay? And it means approximation in soup norm. Just, okay, so I could write it here, maybe I will write it. Yes, for all f holomorphic in a neighborhood of Kn, there exists G holomorphic on Un plus 1, such that G is approximately F on Kn, and that means that given epsilon, yeah, you can find that G so that the soup norm on Kn is less than epsilon. So keep in mind, that this is the only way to prove theorems on the non-compact things. You cut it off.
Well, why doesn't this whole like, why doesn't this?
Oh yeah, I'm glad you asked. So you haven't had so much experience with Runge, so let's talk about it. Okay. The Runge property in Runge. So Runge, when you see the word in pure mathematics, you think of approximation theorems. Runge says this: if Un is, I'll formulate it in our situation, okay, is relatively simply connected. No, Un is relatively simply connected in Un plus 1. I will explain what that means. That's a purely topological condition, okay? If and only if Un is Runge in Un plus 1. And I mean by that what I just said, the approximation property rules, okay? Approximation property. So I have to explain this. No, I think that will answer your question. So when I say Runge in something, I mean this, okay? Okay, just this approximation product. Now you learn in complex analysis of one complex variable, you start with Cauchy integral formula and waste time with some fine proof. So in the end it's a power series, and then you have Cauchy integral formula and all this stuff. Then you have normal form, you have open mapping theorem and maximum principle and all this stuff. And then you prove Mortal theorem, but that's nothing, but you just understand the topology. And this takes a little bit of time. And then the next theorem in the subject is the only theorem after you've established the Cauchy theory is the Runge theorem, which is this theorem, proved by Runge, probably in the turn of the century in the 1920s. So what it means is this, we need to give you an example. Examples, just so you get some feeling for this property. So here's a stupid example, if you don't mind. You take the disk. So this is the thing we're going to be approximating, and the other thing is C. So given a holomorphic function on the disk, can you approximate it to something in C? This is a trivial question with a trivial answer, because if f is holomorphic on the disk, it means that F has a power series development on the disk, which in, well, okay, if F is holomorphic in the neighborhood of the disk is the way I would formulate it, then it has a power series which converges someplace. And this goes to infinity, and as we learned in discussion with this first year student this morning, you can cut this off and go to a finite number, and you get an approximation. That's a polynomial. Okay, it's interesting, it's a polynomial. So it's even stronger, so the polynomials restrict in a good way. Okay, that's a good way. So, let's even go one step further. If you take an annulus, here's an annulus, let's say this is un, and this is n plus, okay, this is un, and let's take a bigger annulus. I'm sorry, you understand what I'm saying, the bigger annulus, un plus 1. So these are two annuli, one contained in the other, one relatively compact in the other, okay? Now notice please that both of these had none, this example here had no topology playing a role. Notice here that both these annuli have a huge topology, I mean they have a circle, right? You see the non-trivial fundamental group. However, if you take a function holomorphic as above, say on the closure of this inside annulus, then this thing has a Laurent series development, right? And from minus infinity to plus infinity, NC to the n. Now, you want to approximate that, and you can do the stupid thing that you just did, some approximation from here to here, not equal approximately, from here to here. So you can approximate that by a Laurent polynomial, and you're finished. Because Laurent polynomials exist on the bigger thing. It's a polynomial, it exists on everything except here, and so it exists on u plus 1, and you're finished. You see that if you take the fundamental group, here we go, of the big thing, of the small thing, and you look at the map of the fundamental group of the small thing into the big thing, right? Well, you see what happens. The fundamental group of the small thing is generated by the circle, and it generates the fundamental group of the big thing also. I mean, it's really wonderful. Okay? They're even isomorphic in this case. Okay? Now let's take another example where they're not quite isomorphic. So that would be the case where the fundamental group of the big thing is bigger than the fundamental group of the small thing. Okay? Look, you don't care. I'm going to make the same example, so the same example, except I'm going to make a whole, so un is as above, and un plus 1, not as above, say un plus 1 hat, I'm going to change it, equals un as above minus a disk. And I'm going to put this, the big disk, so when un plus 1 is a big thing, I'm just going to put a big disk here that has nothing to do with the situation. All right? So as Mihai pointed out, in the original case, these things are isomorphic, but in the second case, you will have, of course, this one circle in both places, but this circle here will have nothing to do with the little thing. So it will not be isomorphic, but what you have is that this mapping is an injection. That's the theorem. That's really a beautiful theorem. That is an incredibly beautiful theorem.
What does it mean relatively simply?
I just told you. Your English language is better than mine, probably. It means, relatively speaking, it's simply connected. It says, relative to this map is injective. It says the cycles here are really cycles here. They do not get killed. Okay? This circle here does not get killed. We should now look at an example. So let's take the big thing, un plus 1, to equal the full disk. Okay? So we have un to be the annulus. And un plus 1 to be the full disk. Right? If you take a holomorphic function on the annulus, it has a Laurent series expansion. You can approximate it with a Laurent polynomial. But that Laurent polynomial is no good anymore. And I can give you a really good one you can't do. This is the first thing you learn in the first baby steps in complex analysis. You better consider the function 1 over z. So you can never approximate the function 1 over z, because if you had a sequence of functions approximating 1 over z, the Cauchy integral approximates. The Cauchy integral of 1 over z is 1. These functions are holomorphic on the disk. The Cauchy integral is 0. So, yeah. So this is the thing, and if you want to think about this, there are many references to this theorem. This is the second theorem in complex analysis in one variable. The first theorem is Cauchy theory and all the corollaries. This is the second theorem, and very, very, very important.
Relatively simply connected means that the fundamental group is a subgroup of the bigger thing.
Yes, the natural map, then you have a natural map. It realizes it as a, yeah, you have.
Here UN is a disk removed, two disks are removed from a bigger disk, right?
Yes,
UN.
you mean in the second
In
example,
the second
yes.
example. But then the fundamental group is F2. But
The fundamental group of the big thing
smaller.
let's do it in this case here. That's what you're talking about, right?
Yes.
The fundamental group of this thing is z plus z.
UN plus 1 was annulus.
Is bigger.
It's annulus, right?
No, the other way around. Un plus 1 is the thing with the disk with two disks. So un plus 1, I'll draw the colors so we're not confused. Un plus 1, I have removed the small disk to make it an annulus, and I remove a little a little stupid disk in some place. Okay? So it has this cycle obviously in the fundamental group, and this cycle obviously in the fundamental group. So its fundamental group is z plus z, and this fundamental group is just z because it's an annulus.
But
Right.
when you cannot do it, like when the UN is not Runge in UN plus 1,
Here,
there's no map that.
there's a map.
Yeah, but
The map's not. The map's not injected. Come on. So the big thing is the disk. Okay. The little thing is an annulus. You take this circle in the annulus, which is non-trivial in the annulus. You say, forget it's in the annulus, it's in the disk. Well, it's homotopic to 0 in the disk. That's this map. Right? This is a map. You just map the curve in there and you consider it there. You have a chance that what happens is, in the bigger thing, you put back the hole, yeah, that caused this circle, and it collapses. That's what happened. You're still, I haven't explained.
I mean
What bothers you here?
the map, the existence of the map, does it always
Okay,
exist?
I'll write down the map. Or I'm going to say the map. Okay. The fundamental group is the pointed loops. So you fix the base point.
I know.
Just a minute. The fundamental group is the pointed loops. Say we have x contained in y. The fundamental group, I take the base point in x. Fundamental group is the base loops at x. Modulo homotopy in x. The fundamental group in y is the base loops at x. Modulo homotopy at y.
Yeah, but what I'm saying is that the fundamental group of the disk is just identity.
That's right.
So what is the map from something that is not trivial to something that is really trivial? Like, I mean,
It's the map that is not injective. It maps something to 0.
maps everything to 0.
Yeah, because it maps everything to 0. So in this case, let me just say the fundamental group of the annulus. I'll write it as an annulus, okay? maps to the fundamental group of the disk by the stupid map, which is 0, and it has a big kernel. Okay? And it violates this. Okay?
Yeah.
Now you get the feeling, and the word relatively simply connected makes good sense, right? Because it means that the stuff's in the small thing really is also in the large thing. You don't lose anything when you go in there. Yeah?
Professor, so UN there is complex plane, let's say.
You mean the first example?
The second example.
No, UN is,
Okay, a disk. Disk with 2 points removed is our UN.
yes.
And UN plus 1 is disk with 1 point removed.
No, the other way around.
Can I ask a question? Does it, when UN is relatively simply connected?
So we're going to discuss this example. I'm glad we're discussing this. This is really important. Okay, this example we're discussing, right? Let me say it again, or maybe I need to formalize it. UN in this case, or I should say A or whatever, is the annulus, okay? UN plus 1 is a concentric annulus, slightly bigger, with another disk removed. I just drew it. Here it has the hole that you have here, but it has another one removed. In fact, I could remove countably many holes here and make it really bizarre. Okay? What thing?
I was going to ask whether relative simply connect.
Relatively simply connected.
Is it equivalent to having fundamental group of the first set being a subgroup of the other?
That is the definition of relatively simply connected. Okay?
So
Maybe I didn't write it, but that is the definition. Okay? Are you okay on this, Qaisar? Okay. Kevon, is it okay?
Yeah.
Okay, but the fact that Runge's theorem is true, fundamental theorem, that is equivalent to the topological condition. It's an amazing theorem.
I never thought about this in this way, but another definition is you look at the complement, and if the complement.
That's right, but the point is you look at all this complement stuff, and you read that in some book about complex analysis, and it hides the truth. It hides the topological condition, really. The statement is the connectivity components of the something about the connectivity components of the complement. Yes, but these are for people who don't like to think topologically. I don't like that definition, but in fact I have to use it occasionally. It means the fundamental group injects. Punkt. It's an incredible theorem. One thing is Runge and another if and only if the fundamental groups inject. The one condition is purely topological, the other condition is purely complex analytic. Okay? That's an exciting theorem. It's the second theorem in complex analysis. The first theorem is Cauchy theory. Okay. Maybe normal form, maybe it's the third theorem. The normal form theorem is maybe should be regarded as the second theorem, and this is the third theorem. Okay, let me show you how to use Runge's theorem. Okay? Oh, here it is. Okay. Now, I'm going to have fun. Recall what I want to do. Given a function H on some open set, we wish to determine another function G on some open set, on the same open set, with the correct partial derivatives. Partial H. So partial G equals. Okay, You should always think like a physicist and say, let's solve this problem formally. Probably is good enough for our purposes. Let's see. So, proof.
This is Z bar, right?
Huh?
Z bar.
Z bar. Proof. So I'm going to use aromatic exhaustion. Let UN be aromatic exhaustion as above. Okay. So I have a good exhaustion, and let's let, the thing is, let's let chi n cut this thing off on UN, so I haven't done anything on UN. So I'm going to graph chi n, here's UN, and chi n will be 1 here, and go down to 0 here. And here someplace is u. And this height here is 1. And this is u. So that kind of cutoff function. And now let's look at let Hn be as above, be the double integral, so as above, so Hn of zeta, I guess I call it, Hn of zeta, be the double integral as above.
Should it be Gn of zeta?
Probably, absolutely. Hn we need inside and Gn outside, right? Thank you very much. The double integral as above. So that solves the problem. Well, that's good. So now you say, okay, you should be very optimistic in general. So you'd say, let's take the limit of the Gn. So the Gn, I didn't do anything on UN here, right? So this solves the problem because the limit of the Gn should be equal to 8, right? I mean, I keep getting better and better and better and better and better, right? Because it does the right thing on UN, but it didn't on UN plus 1 as well, but I just go on. But of course, you write this here with a big convergence problem. There is no reason that this sequence of things converges, Gn. Okay? But you should be courageous and write it down. Now, there's only one technique here that I know that works.
Professor, I have a question about your definition of Gn. Should the h inside integral to be h?
I'm sorry, absolutely. So I cut it off, and I didn't define what the heck here, I should write here Hn, right? And Hn is chi n times h. That's what you mean, Centel, right? Yeah, I cut it off and I solved the problem. Right? So thank you very much. I cut it off, solved the problem, and I'm going to take a big limit. There's a huge, I cannot control the convergence. So there's a completely standard technique that's extremely useful. Otherwise, I wouldn't bother telling you the proof of this. You know this technique, but let me remind you, it's called the Kepler method. No, Galileo method. So I prefer the Italian viewpoint. This is very Freudian to talk about viewpoint because I'm looking through a telescope. So you write Gn as equal to Gn minus Gn minus 1 plus Gn minus 1 minus Gn minus 2 and so on. You know this method, right? It's called telescopic series method. That's the reason I call it Galileo method. Have you been to if you have a chance to go to the museum in Florence at Galileo, where you see these fantastic telescopes and so on, it's really interesting.
Do you use a different character?
Huh?
You repeated Gn 2 times.
I did. Let's see, Gn
Vitamix.
minus Gn minus 1 plus Gn minus...
Gn equals Gn minus.
Gn equal Gn minus Gn minus 1 plus Gn minus
This
1.
isn't this called Aldo summation?
This I call telescoping series.
Yeah.
Oh, okay.
This is telescoping series. The point being that we write Gn equal to some something gk minus 1. Right?
You have to define G0 to be 0.
Yeah, you define it the right way, don't worry about it. And then you need to understand whether this series is going to converge. Okay? And now you need to think very slowly what that means. Right.
You put it in the integral.
No! You never prove anything with an integral because it doesn't converge. It simply doesn't yet converge. It is simply trash at this point. Okay? Simply trash at this point. But you should remember what this thing is going to have to be. It's going to, you want it to converge. What does it mean? On every compact set, it should converge. So give on every compact set, it should converge. Okay? So you want to estimate these things, gk minus 1, on compact set. Sup norm, use triangle inequality, push it through. Right? Sup norm on this thing. Right? And it's going to be trash. It won't converge. But you have freedom. This is not like in the old days in the Soviet Union or something where you can't leave and go to spend some time in Berlin in a nightclub. Or even better, going to Bangkok to the celebration of water and so on and have a good time with beautiful girls. The Thailand girls are really incredible. So, yeah. Yeah, you have freedom. And the freedom is, what is in the kernel of this operator? You don't care. The solution is not unique. Right? The solution is not unique at all. You may adjust, you see, you may adjust the solution by gk. It's your old gk. This is like me, I'm old. And then you can, you young guys come here, and you make some modification, fk or something, which is holomorphic. And the key is it has to be, you want to, now look, this difference here, look, this difference here, d bar of this difference is 0 on k minus 1, right? It is holomorphic on k minus 1, I don't know, I'm sorry, I have so many k's here, but it's difference is holomorphic, right? And all I'm asking to do is approximate it by a holomorphic function on the next thing. Right? So that's okay. So I make this approximation so that gk minus 1 is on sup norm on kk minus 1 less than 1 over 2 to the k. I'll add it up. Okay, it didn't work. I'm sorry, well, maybe whatever you want. I don't care. 1 over the 2 to k will do. Because you see, this needs to be Cauchy. This will do it. You see, this sequence needs to be Cauchy, and really, if you start with this telescopic series Cauchy, means you're cutting off everything down here. So you really only talk about top level terms. So that's it. Again, Runge, and you need the existence of a Runge exhaustion. So you need it to prove that given any domain, you have an exhaustion by open sets which are relatively connected as you go out. It's a little bit of fooling around to really prove that, but you can do it. It's really, really interesting and really, really important. So this is my proof, I guess most people's proof, of the Dobol lemma. in dimension 1.
But I have a question, how could this technique help with the limit thing? Because we want to show that the limits of Gn is exactly the G we want.
Yeah, I didn't change anything in terms of that. You see, I only added something that is killed by the d-bar operator. So you see what I'm saying? Look, what we want is that, right? So the original sequence is good on each set. This sequence is also good on each set because I only changed it by a holomorphic thing. You see, it may be yeah?
This question is, how do we know that the limit function is good?
It's the uniform limit, I mean, it couldn't be any better. Okay? I mean, it's a very strong limit, yeah? Okay? I think it's a reasonable question, actually, Sindel. I think actually one has to think, I mean, I think you really have to, it's true, it's okay. But I think you have to think about the regularity and things like that. I think that's what you're asking about. I mean, right?
But I mean, you're passing to the limit and you're differentiating. So I think.
Yeah, but you see,
I mean,
you don't forget what you're doing. It looks like you're doing something terrible in the C infinity situation. That's what you're saying. That's what Sentell is saying, I think also. But don't forget what you're doing. On compact set, if you didn't make this change, you have a representation of this function in a good way, right? By this integral. You see? And what you're doing is changing it by a holomorphic function. Where with the soup norm calculation, then you're in business with a holomorphic function. You're not worrying about it. So that's a little bit delicate. I think that's
Yeah, because my question is that we need to check that differentiation of G with respect to C bar is that
formally it's obvious, but if there's some question about the differentiability of the function. And what I just said is if you didn't have to adjust it, you see with this convergent business, then it's trivial. It's almost formal. But what I adjusted it with was a holomorphic function. And then you know the soup norm topology of holomorphic forces the derivatives to all converge. So you're in business. So, but it's a good question. Okay? Yeah, thanks very much. Well, I'm happy that I took the time to prove that.
Professor, my question from the beginning was, since your normal d by dz operator still satisfies d squared equals 0, why didn't you go in the other direction and work with sheaves of type 1, 0, not 0, 1? Why is the d bar so special?
Yes. So he's asking me why didn't you use the other operator?
I mean, everything I think works with the other
Absolutely, except for the first step. And the first step is this. Recall, the first step here, original thing, is given is a holomorphic vector bundle. Right? And this has transition matrices Gij. And these things are maps from, as you know, from Uij into GL and C. And these maps are holomorphic. Right? I mean, that's just it. And now we're talking about sections of this thing. Holomorphic sections of this thing. Holomorphic section of this thing is a collection of sections on local trivializations which satisfy this thing. Right? So far, so good. Now look what happens. If I tell you I'm going to use a d-bar operator, you're going to say, hey, you're in business because this thing is holomorphic and the d-bar operator treats it as a constant, right? So that means that this d-bar operator maps holomorphic, makes sense on this bundle. It means that the d-bar operator really defines
another section.
the holomorphic sections, right? If I took the d operator, first of all, it wouldn't make sense because it wouldn't go through this thing as a constant, right? I would have to use a chain rule here, and it'd be horrible. Not chain rule, product rule, right? But here, this thing is constantly with respect to D-bar operator. Okay? That's great, my didactic improved by a big thing because of your good question. Okay, so that was Gobel's lemma. I could have gotten around all of this Runge here, but I really wanted to explain to you this Runge here, and that's it. And Grothendieck wrote down sort of an induction argument, which is not so easy. So, Grothendieck proved the Gobel lemma for polygons. So, in dimension and constant. Okay. So, that's the conclusion of all of this. We spent a lot of time, but I think it was valuable time. The conclusion is that this resolution of the sheaf of germs of sections of a homomorphic vector bundle with the D-bar operator this resolution is acyclic. Is acyclic. There is no cohomology of this resolution. Okay. It's acyclic at the sheaf level. Okay. Very good. Okay. And now we define the Gobel cohomology of X, not only H1 but HQ, with coefficients in the vector bundle to be the kernel of the D-bar operator from sections from differential forms. So let me just write it here. Sections on X of 0T forms with coefficients in the bundle. This would be the usual definition of this sheaf or vector bundle. Usual notation. Which is 0T forms, T plus 1 form. Well, no, let me write. I got ahead of myself, I'm sorry. Okay, so that's the Gobel cohomology of this thing. So I shouldn't have written. I got it. It is acyclic, but let me. This is not what I wanted to say at this stage of the game. I'm terribly sorry. This is an exact sequence of sheep. This is exact sequence of sheep. Okay. That's all I proved. It's the Gobel lemma says locally given a closed form, it's exact. Right, that's the Poincaré lemma for the d-bar operator. The next step is exactly what I want to say, is that the double exact sequence. So the theorem is this, is the double exact sequence sequence above is acyclic. That means acyclically in check cohomology. I'm sort of explaining to you a machine for computation. You start out with a good resolution. It's really complex. You have to prove a local lemma to say that it's really exact. It's an exact sequence of sheaves. Then you're in business locally, there's no cohomology, everything's perfect. Then you write down the global cohomology. You're going from local to global always. Then you have an interesting cohomology theory. And the key is then, in this case, that this sequence is actually the sequence of sheaves is exactly acyclic in the check cohomology. This means a cubed of x, well, let's say HL of H of this thing. So if you use C infinity things, all of these cohomologies vanish for L positive, and, well, and also an NAQ. So this is what you will see. This is what you want. It's a theory that works always. So write down the resolution. It's local exact. That's great. Write down the cohomology. We need this acyclic. But I don't have too much time. Let me just give you an example of how to have fun with this. So, e.g., tomorrow I guess I'll start with this, but let me just start now talking. So, suppose, let's say that I'm interested in H1. I take a Laurent covering, okay, of say, of just functions, C infinity. And I want to show you that on a Laurent covering, the double cohomology with C infinity functions is 0, H1. How would I ever do this? Okay, it's a reasonable question. Okay. Watch. So what is given to me is a collection Fij of smooth functions on the intersection. And the double question, or the cohomology question, is this thing the difference of Fj minus Fi? I've talked about this many, many times, right? This is really the question. You're given a cocycle, is it a coboundary? That means it's it's just some silly question. You have two intersections, you have Ui, Uj, and you have Fij here. And can you take something that's defined here and write it as a difference here? This is a completely trivial thing to do. The trouble is that you have all sorts of things everywhere going on, and you have to solve this problem for everything. It's huge. Okay? Well, it turns out it's very easy to do. So we let key I be a partition of unity relative to this covering. Okay?
U is, what is U? Is just an open set?
No, let's start again. I said it but didn't write it, I'm sorry. Let U be a Laurent cover.
Okay, Laurent cover, okay.
Because I want to prove the cohomology vanishes. So I need to start with a covering where that's it.
I see, so this is a check cohomology.
Yeah, that's the whole thing. I should really even, but I'm talking about this thing being being,
Okay, so if you X and then you have the right cover and you want to show that
the homage is
the
zero,
homage is zero. Okay.
okay? I'm taking the example of smooth functions only. That means on this cover, every intersection gets hit with a smooth function, Fij. This is really simple-minded question. Here's the question. Given, see, everything's getting hit, but, right, with Fij. So the question is, can you do this? Well, for two things, I mean, anybody can sit down, I think, and do it. But, right, but for many things, it's not so clear. Really? It is clear, actually, if you think about it a little bit. You define Fj, you won't believe how trivial this is, as, and now you have to think a little bit more than I'm just saying here, but it's really, it's really this. So, okay, so to get this right, I maybe have to take a double cover so that I shrink the Fij's a little bit so that they're defined in the neighborhood of the closure. You have to worry a little bit about this kind of thing, and then cut them off with the partition of unity. And so that the thing inside of the summation is globally defined. It's globally defined, locally finite. This is nothing. So this thing exists. And now, I will probably get the sign wrong, but look, Fj minus Fi. I'm going to write it down. It's really silly. So that is sum chi L Flj minus Fli. Now Fli, so Flj minus Fli equals, I'm going to twist this around, Fil plus I twisted it around, Flj, yeah, and I've got the wrong sign, I think. As you know, if I add Fil plus Flj plus Fji, I get 0 because it's closed. So unfortunately, this equals, what does, oh no, I lucked out. I lucked out. This is equal to Fij. Yeah. So this is equal to Fij. So this is some chi L, Fij, but Fij has nothing to do with L. L runs, that's a partition of unity, the sum is 1, so this is Fij. So if you have a partition of unity, and the French talk about, the French word is flasque. So, and the translation of flasque is maybe like I am, flabby. So if you have flabby functions which you can push around with a partition of unity like this, then you can always prove vanishing theorems. Okay? And so you see it's purely formal. I just pushed around with partition of unity. And the higher order terms
Is
also.
that thing defined in new G?
What?
Is that thing defined globally on new G?
Yeah.
FG.
You mean this, what? These functions?
This is only.
Yeah, sure, I cut off everywhere. Yeah? And I mean, I cut off an extent. I didn't say it, but I'm sure I'll extend. All right. So, I mean, well, I mean, I'm only asking that it's defined on, that's what you said, Mihai, on UK. In fact, it's even defined everywhere. Right.
But the higher homologies are probably zero as well, right?
It's the same thing.
It's the same.
Everything's the same. So I don't think I'm bothered proving it. It's just for C infinity things. Use the French word flasque, where you can push the functions around by cutting off and doing stuff. You can have an argument like this always. Okay? And so these things always vanish. And that is the other key ingredient. So d bar squared is 0. Locally it's exact. That's a Poincare lemma or a double lemma of some sort. Acyclicity, which is this, is the flaskiness of the sheave. You can use partition unity. Okay? Those are the three things. And you're off and running. So tomorrow I'll show how to use that. And I'll show everything tomorrow. I'll start getting close to some serious results with this. But I thought you should see the technology a little bit. Right?
The Runge thing is really nice.
What?
The Runge thing.
Yeah, the Runge thing is one of the most beautiful theorems. This is the most beautiful theorem of the day. And it's really neat. I mean, it's really, really neat. Right? I don't know how I proved it. Really, I know how I proved it, but I don't remember how I proved it. Probably pretty serious.
Does it have a generalization in that?
What?
I mean, does you get your, analytes?
I missed the first part of your
Yeah,
question.
I mean, does it have a generalization, higher dimension?
Yes. And it's fundamental. This was fundamental for Oka's work, absolutely ingenious work in complex analysis before the war, and from Behnke and Stein also understood the importance of this before the war, and then after the war, Grauer just exploded this into some really deep mathematics. And after this, Gromov looked at the Grauer paper and really even took it much further. So it is a connection, it's called the H principle of Gromov, and H stands for homotopy, and it's somehow this comparison between homotopy phenomena and approximation phenomena and results in complex analysis and so on. Grauer's, that was Grauer's, by the way, that was Grauer's habilitation at a very young age. Unbelievable. The principle at the highest level would be called Grauer's Oka principle, and it's really very deep Runge theory.